from the optimization notes. As a reminder, make sure you are trying these problems yourself first before you watch each of these work-throughs. Okay, try them yourself, and then when you get stuck, come here, or when you want to check your work, come here. All right, example 5 says, in a swim and run biathlon, Jill must get to a point on the other side of a 50-meter wide river 100 meters downstream from her starting point. She can swim at a rate of 2 meters per second and run at a rate of 5 meters per second. Toward what point on the opposite side of the river should Jill swim in order to minimize her total time? Okay, so step 1, we want to read the problem carefully. All right, we want to understand it. So Jill is swimming and running a race, a biathlon. The swim is first. She gets to choose at what point on the opposite side of this river does she swim towards. All right. Once she gets to the other side of the river, on that shore, she's going to run to a point that's 100 meters down from where she started, right, on the opposite bank. So we're given her rates for swimming and for running. And it's our job to find where, like at what angle or how far down the other side of the bank should she swim. Okay, should she aim for? So, reading question, understand the problem. All right, step 2, draw a clearly labeled picture and label it. We're given just kind of a rough outline of the situation so we can get a visual on it. But we definitely need to add some information to this. So her starting point is here in the bottom left. It tells us that it's a 50-meter wide river, so make sure that we add that. That's important. And that it's 100 meters down on the other opposite side of the bank where the finish line is. Okay, this diagonal black line in here is just an example of where she could swim to. Just like in the last example where the rectangle was just an arbitrary rectangle, this is an arbitrary point. It doesn't mean that it's going to be at that angle. Don't measure it. Don't pull out your protractor. All right, so what we want to find is how far down the opposite riverbank should she swim to. All right, so if we label that value X, that's our unknown. That's what we're going to be looking to find. All right, and we can go ahead and make our box. Go ahead and make our box of what our final answer should look like. All right, Jill should swim to a point blank meters downstream to minimize her total time. All right, so then filling in the rest of our diagram, if this is X, then the amount she's going to run, right? So she swims this far. We could label this length. I label mine H. You could label it whatever you want to. That H is the length she's going to swim. I've got that labeled here on my variable descriptions. X is the downstream distance, so that means that whatever's left from that 100 meters, so 100 minus X, is how far she's going to have to run. Okay, so we're going to have multiple secondary equations on this one. Let's see what else we need to do. Identify variables. State what we're trying to optimize. Right, an optimization equation. All right, so we're trying to optimize time, right? This is the first one we're trying to minimize. So we're trying to minimize her total time. So how do we calculate her time? So her time is made up of how long it takes her to swim plus how long it takes her to run. Okay, so I set up this this basic total time equation here and just made total time as T and her swim time S and her run time R. All right, so it's just the sum of those two times. So now we have to break that down and find how to secondary equation for her swim time and for her run time. Okay, for her swim time, since we know the rate of her swimming, we don't know her distance, we want to find her time. then think about our dirt formula. Distance equals rate times time. All right, so that's a secondary formula, just like area or perimeter or Pythagorean theorem or trig ratios that I want you to be able to call on. Okay, distance equals rate times time. We're given rate. We can probably find the distance in terms of some variable. The time is what we want. So if we take that and we solve it for t, then we get time equals distance over rate. You guys did a bunch of these problems in middle school and Math 1 of a either a direct or inverse variation functions. All right, so distance. That means we need to find distance. We know the rate is 2 meters per second for swimming. So to find the distance, if we see that this is a right triangle here, formed by the 50-meter side that we know, the width of the river, this value x that we don't know, but it's a variable x, and then this side that I labeled h, then h is the distance that we need. So we can set up a secondary equation for h, and we can say h is, and then use our Pythagorean theorem, right? We know one side. So let's use our a squared plus b squared equals c squared. So h squared equals leg 50 squared plus other leg squared, x squared, and square root both sides to solve for h. So we get a, secondary equation for h. All right, that is in terms of x. All right, I started off by just saying it was h over 2. Again, 2 coming from the swim rate, h is her distance, and then we can plug in that value in terms of x for h. Okay, and then for the runtime, for our capital R, the distance is going to be 100 minus x, and our rate is 5. So our runtime is going to be 100 minus x over 5. Okay, so now we've got both of those secondary equations in terms of x. Now we can plug those into our optimization equation. Okay, so if we plug each of those in, then we get this guy here in purple. Again, we got our function in terms of one variable x. So now we can put that into a more differentiable form, knowing that our next step is going to be to take the derivative of it so that we can find the critical points. And so rewrite that square root, rewrite that divided by 2 as a 1/2 coefficient, and then take that fraction 100 minus x over 5 and split it into a constant and a variable term. Before we take the derivative of that, one thing we skipped over was our constraints for x, since x is our independent variable in this. So let's go back up to our picture and let's consider our constraints. So x is the point from directly across the river that Jill's gonna swim to. That whole side is 100 meters. So it's got to be between 0 and 100 meters. She could choose to swim straight across the river and totally minimize her swim time, but then she has to run that whole 100. Okay, but that's a choice, and so we want to consider that. We want to include that 0 as an endpoint. All right, this is the first example we've looked at where we want to include our endpoints in our consideration for our extrema. Okay, and then the same thing, or the opposite thing. She could choose to swim all the way to the end and not run at all. So that would be her x value being all the way up to 100. And so we want to consider that not just between 0 and 100, but also considering she could do those extremes. So there's our constraints for x. So now when we go to find our critical points, going back to our t, we take the derivative by hand, going one term at a time. Be careful of your chain rule. then we want to consider both our critical point and our endpoints. And so I would go ahead and build out a table and put your endpoints in there. And let's see, to find our critical points, we want to set our derivative equal to 0. Excuse me. This is what your calculator is for, right? With an equation like that, put that into y1, graph it, find that 0. There was just 1 0 there at 21.822. Looking for where our t prime is undefined. Don't rely on the graph of this to find where the derivative is undefined. All right, do it algebraically. So I see a denominator here. So set that denominator equal to 0. And we're going to find there's no real solution for that. The restrictions for the radicand are going to be outside of our domain of values. So we don't have to worry about the restrictions for that one, similar to the last problem. Okay, they're not going to change our answer. All right, so our only critical point, 21.822, and our endpoints, plug all three of those points back into the original, back into t, to find out what her total time is for all those three. Okay, so we don't have to actually do a sign chart on this one, since these are the only 3 points where there can be extrema. Check all three, and again, we're looking to minimize time, not maximize. We're looking to minimize, and so that minimum value is going to come when she swims 21.822 meters downstream to the other side of the river.